Chingo. No diga ahí la afiliación, pues. No diga ahí la afiliación. Omite la afiliación. Vale, sí.
Bueno, primero, gracias por venir. Gracias a la gente que nos fue acompañando desde el semestre pasado y agradecer a la gente nueva que se está uniendo en esta ocasión. Para primera charla y también queremos presentar a un nuevo miembro del equipo, Mayito. Sí. Así que ya vamos a presentar a...
Tuve el agrado de presentarles a un gran amigo, a Gabriel Arenas. Él hizo su pregrado en la Universidad de Valparaíso, la Universidad Católica de Valparaíso, para luego hacer su máster en la Universidad de Quito con la profesora Gabriel Arenas. Y actualmente acaba de terminar su doctorado en la Universidad de Arenas, en el Reino Unido, y eso es de lo que nos va a hablar Gabriel.
Okay, thank you. I'm going to talk in English because I think that that's the way that we should talk. Thank you very much for inviting me. Actually, it was like a self-invitation because I was pressing a little bit to give this talk. What I'm going to talk is something that I've been doing the last 4 years, I think. It's related to these accelerating black holes, and in particular in the case of 3 dimensions, 2 plus 1 dimension. And this is, there is a series of papers. The first one came out in 2022 with my supervisor, Ruth Gregory, and Andy's Coins. And the second paper just came out, I don't know, like less than a month ago, I think. It was with Adolfo Cisterna, who is in Prague. Felipe is there, and also Ruth. So let me, oh, what's happening? Anything? Oh, reviews. Oh, there. Yeah. Okay. So let me just, this is the outline of the talk. I will start by start with a motivation, and then reviewing a little bit of accelerating black holes in 4 dimensions, which is the standard thing. Most of people that knows about accelerating black holes knows about them in 4 dimensions. And then I will move to the 3-dimensional case. So let me start by motivating this. The first thing is that when we talk about accelerating black holes, these are not astrophysical black holes. This is purely theoretical. And the way that we make these black holes to accelerate is to attaching this black hole with a cosmic string. This is an extended object that sort of pushes the black hole from the boundary, and it extends from the deep interior of the space-time to the boundary. So this object, this codimensional 2 object, which is called a cosmic string, produces what is called a conical deficit, and this conical deficit is the one that is related to the acceleration. So this is not, I've always received this question that are these astrophysical black holes? The answer is no. Okay. And what it does, this acceleration actually, in the case of ADS, is it deforms the structure of the space of ADS in this case. Okay. And as it deforms the structure of ADS, it's very interesting from several topics. The first thing is in 1999 there were like a boom of a lot of papers relating to brainworm type of black holes. There is this famous series of papers by Emparan, Horowitz, and Meyer, where they find a way of slicing the symmetric, which is the one that describes the accelerating black holes, in such a way that you can localize a black hole in 1 dimension less over a brane. So those are what is known today as quantum black holes. And there were a lot of holographic applications after this series of papers. And then there are another type of applications, like holographic applications, just taking the symmetric and seeing what is the boundary description associated to the symmetric. There is this the first paper by Hubeni, Marov, and Rangamani in 2009. They were trying to find a dual of some strongly coupled systems that are localized on curved backgrounds, and they find that the symmetric is the one that should be the bulk dual to these strongly coupled systems. And then there is like a sort of gap of papers until Ruth and her collaborators, Andres Navalon, Michael Aples, David Kubishnak, Rob Mann, published this another series of papers where they describe the accelerating black holes from a holographic perspective, and they do the thermodynamics, all the thermodynamics of these black holes. So it's been a lot of interesting results in the last few years. The next point is related to how you can embed. If you want to do a holography, you always have to ask, is this embedded into a string theory in some such a way? And this question was answered by these people, by Jerome, Ferrero, Piña, Martelli, and Sparks in a series of papers. They've been doing this mechanism of wrapping brains into something that is called a spindle. So you can have, like, let's say, D3 brains wrapped in a spindle, which produces some type of geometry in the IR. In this case, an accelerating black hole is produced when you wrap M2 brains on the spindle. And they find that you can actually uplift these kind of solutions to M theory, and you find something that is completely regular, as it should be from the point of view of the string theory or an M theory. So these solutions are embedded into a higher kind of theory, and it's been one of the big kind of areas or topics in the last few years. Actually, this week there were a couple of papers by them talking about this kind of spindles. And the last question is more related to the three-dimensional gravity. So pure gravity in 3 dimensions, it doesn't exist as a quantum theory. This is a paper by, this is a statement that it is in the paper by Maloney and Witten, 2007, where they show that if you compute the quantum partition function of pure Einstein gravity in 3 dimensions, you find that it is not a consistent theory. It's not a consistent quantum theory. And instead, you should add there should be some unknown contributions in 3-dimensional gravity. So they propose different ways of solving this problem. One of them is considering extra content into the theory, and they propose that it might be a sort of cosmic string or domain wall. In the case of 3 dimensions, the only thing that you can add is a codimension 1 defect. If we are in 4 dimensions, you can add codimension 2 defects. In 3 dimensions, a codimension 1 defect is a domain wall. So they leave this question open, that perhaps you need to include this kind of contributions to obtain a consistent quantum theory in 3 dimensions. So these are several questions that one can have, and that are related to the fact that we have these sort of solutions in gravity. So let me start with the 4-dimensional accelerating black holes. The 4-dimensional accelerating black holes were introduced many, many years ago. Actually, there is a yeah.
We're talking about accelerating black holes pulled by a
yeah.
So can you imagine if you have an accelerating space time, you will generate this ring that way.
Yeah.
Can you imagine putting a black hole in an accelerating space time, which is not quite the same situation that you described? Has someone done that problem?
Oh, I'm not entirely sure. Yeah, I think that this. I'm not entirely sure. Yeah, I think that the mechanism to accelerate the space-time will be different. I'm not. Yeah, it will be. Yeah, I'm not entirely sure, to be honest. Yeah. We'll need to think about it. Yeah.
the contradict the one that declares the so that the reason of this is actually because the death actually determines the tension of
Yeah. I will go back to, yeah. I think that it will be more clear. Yeah, it will be more clear in the next few slides. I just wanted to give you a sort of preview of what. Okay. Yeah. No, it's a very good question. Yeah. I will answer that in 2 slides. Okay. So the accelerating black hole in 4 dimensions, the original version of this thing, it is the symmetric, and the symmetric was discovered by Levi Civita in 1918. So it's a very old thing, but it's been rediscovered over the years. And the most known version of the accelerating black hole metric, it is encoded in the Blavatsky-Demiansky metric, which is a solution found in the 76, that describes a pair of black holes that are charged, and they're accelerating between each other. So there is a cosmic string connecting these two black holes. I will be interested in just having one black hole, so one can eliminate one of the black holes, but you still have the cosmic string. And as Rodrigo says, as these black holes are accelerated, they are disconnected by this ringed horizon. And the metric that Blavatsky and Demiansky wrote, it has 7 parameters. It is the most general solution to Einstein-Maxwell equations. It has mass, a knot parameter, angular momentum, electric and magnetic charge, cosmological constant, and parameter 8, which is related to the acceleration. So it's a very complicated metric. A lot of people like that, but I don't like that much. So I prefer just to keep track of these 3 ingredients: mass, parameter 8, I will call just acceleration, and cosmological constant. And I will focus on negative cosmological constant. So the metric looks like this. This is the metric of an accelerating black hole. The first thing that you have to notice is that here it looks pretty much like a charged black hole, but with a couple of things, couple of peculiarities. The first one is this conformal factor outside, which sort of acts as a deformation of this spacetime, and you can see that it depends on 2 coordinates, r and theta. Okay. So the second point is here encoded in this part. This is the angular part, and usually in a charged black hole you have an S2 here. So to get an S2, you have to turn off this term, which is related to acceleration. So once you accelerate, what you're doing is you're sort of deforming this S2. So this object is what Jerome and his collaborators have called as the spindle geometry. Is like a S2, but do I have a, yeah. It's like a S2, but it's deformed in this way. So you have 2 conical deficits at the north and south pole, which are connected to this label K that I put here explicitly. So we can see that this is the function of the metric, and the parameter K is the one that is related to these conical singularities at the north and south pole, and at the same time, as Yorgos was saying, this is connected to the cosmic string tension. So the conicity of this term is the one that determines the tension of the cosmic string going over the space-time, and is given by this. So you have 2 different tensions at the north and the south pole. And that difference of tension is the one that produces the acceleration of the black hole. So yeah. No, you need you know both.
They're very similar. One by the
Yeah.
You are able to eliminate
Yeah. That's exactly what I'm going to do. Yeah. Yeah, you know a ratio between them, actually.
That's you can fix like sort of constraints of this by a ratio of the tension. So you have yeah.
Okay, so I have two conical deficits, both have different tensions. And what I want to do is what Rodrigo is saying, I want to eliminate one of them.
I can always regularize one of the axes
by choosing
the other one to be like sort of. It's exactly the same as a Misner. The difference with the Misner string is that the Misner string has closed time like curves.
That's the main difference with what Rodrigo is saying. So here I'm killing one of the axes. So let's say I'm going to regularize this one.
So I have like something completely regular, like okay, completely regular, and I leave the conicity just at the south pole.
And this gives me one tension, so I have one tension. And what I want to see is basically I want to see what is doing this parameter A. This is the best way of doing it. I will take the massless limit of the black hole. Okay. So I shrink this to a particle. Okay. And then what I end up is with something like a render type of observer. So this is what is I will fix something that is called the slow accelerating limit. I'm just taking a square L square less than 1. And I can introduce this coordinate change. And what I get is just
ADS spacetime. This is pure vacuum ADS spacetime. Why I'm doing this?
So because I can plot this
into the
Poincaré disk, and this particle that I shrink this into a particle, and I can sort of see how the ADS spacetime is deformed by this parameter A. So so if I take r equal to 0, this is not exactly the center of ADS. In fact, it's just a particular value of this big R, or in the other way around, particular value of this R, big R, is the center of ADS. And as I increase the parameter A, I'm pulling
the particle closer to the boundary. So I'm moving the black hole closer to the boundary of ADS. So that's what the acceleration is doing. Is just the tension of the cosmic string is just pulling the black hole closer to the boundary.
So one can see this as a sort of off-center perspective of ADS. And okay, this is again. Stop. See? So the black hole, what I will focus here is not the full description of the accelerating black hole. I will focus on something that is slowly accelerating, which is basically a black hole that is suspended
off the center of ADS. So why I want to focus on this?
Because in this case, the black hole will remain static,
and also the whole system will be in thermal equilibrium. So I want to analyze something that is in thermal equilibrium.
Okay, so this is exactly as like Newton's law. Wrote a very nice review in 2017. I think that this is the battery is dead.
Okay,
so as this is in thermal equilibrium, I can do thermodynamics, standard thermodynamics. Yeah.
So, you know, when
yeah. Yeah. I think that the fall-off difference is nothing. It's the same fall-off. I mean, it's just a fall-off. Yes.
Oh yeah, that's the difference. Yeah, that. Oh, but there's 2 long questions. Yeah. Yeah.
Yeah, the difference here, and just to let everything clear, is that this boundary, or this boundary, is not. This is very important. This is not the boundary of ADS in the sense that you are taking R to infinity. This boundary is defined by this function, omega. So what is then the conformal boundary? The conformal boundary is defined by R equal to minus 1 over a cos theta. So the conformal boundary is a hypersurface of theta. So that's the main difference between ADS and these black holes. So it's a bit different to the standard case. Okay. Yeah. So yeah. In the standard sense, in this, yeah. Thank you, Felipe. Yeah, that's a very important point. Okay. So what I want to do thermodynamics and I want to do holography. So I will analyze this slowly accelerating black hole. And as it is in thermal equilibrium, it follows the standard thermodynamics rules. The temperature is given by the standard Euclidean method. Looking at the regularity of the time Euclidean coordinate, there is some entropy associated to the black hole. In principle, I forgot to tell you that in principle, the accelerating black holes has two horizons. There is the black hole horizon and there is the Ringler horizon. So as I fix the slow accelerating limit, I'm getting rid of the Ringler horizon, so I just have one black hole horizon. Okay. So there is the standard entropy. And what about the mass? There are two ways of computing the mass. One way is the one that Rodrigo is saying. You can have the electric part of the Bayes tensor, and you can compute the mass using the Astekar-Magnon-Das formula, or you can do the holographic way, as this solution is asymptotically ADS in the sense of the conformal boundary that defines this conformal structure of the metric. One can do Pfeffer-Graham expansion, but in a non-trivial way. The Pfeffer-Graham expansion here is for both coordinates, for r and theta, because these coordinates are not, r is not perpendicular to the boundary. So I need to expand these two coordinates in a common coordinate here, set. So I will do this expansion. We have these f and g functions that are unknown, and by fixing some fall-off conditions, one can always determine these two functions, except for f1. So this is very similar to just doing Pfeffer-Graham expansion. There is always something that is unknown. So we have this f1. We rewrite this f1 in this way. I will just mention that this omega is where I will encode all these the information that I don't know about the boundary, which is called the conformal representative. I can just choose a particular conformal representative of the boundary metric. This is standard. And then my boundary metric is written in this way. So I can do everything that the holographic dictionary says. I can use Bala-Subramanian-Krauss to compute the stress tensor. And then the stress tensor gives me a very peculiar form. This was written by Hubeni, Marov, and Rangamani, and also by Anavalon, Apels, Gregory, Kovich, and Mann. So the stress tensor of the accelerating black holes in 4 dimensions has the form of a fluid, but with some dissipation happening here. So the dissipation is, there are corrections here that are called non-hydrodynamic corrections that appear here in front. Is this D? There are another corrections here related to the cotton tensor. These are like shear type of corrections. There is some universal term which is related to the CFT, blah, blah, blah. And there is not that much else to say here. But what is important is that I can use this stress tensor to compute the energy by taking the TT component and integrating. the only role that plays is that you can sort of rewrite the stress tensor in this way. Nothing else. Be- Mm. This is the cotton sensor of the boundary, so it's nothing else. It's just a way of rewriting the information of the stress tensor. Yeah, yeah. It did, yeah, yeah, that's true. This is just the cotton of the boundary, and as Yorgo says, this is not conformally flat, so the cotton exists. So you have when it's conformally flat, the cotton is zero. That's true. This is just a way of rewriting the information of the stress tensor.
The point is out one way of making
I mean, this is just cotton tensor of the boundary metric, nothing else. It's not related to the theory. This is just the boundary metric. I can have Riemann tensor, I can have whatever tensor I want. It just depends on the dimension. This is just the cotton tensor of it.
okay, we can
Yeah. Well, this C is the cotton tensor of the boundary metric, nothing else. And what I get is just by integrating the energy density, I get the mass of the black hole. What is important here is that the mass also depends on the value of the conical deficit. Okay. And depends also on this beta. This beta is very important because is sort of encoded into the time coordinate. So if we look once again into the map of this metric, so we had something like this. Um, so when we map to global EDS, there is the freedom of adding this rescaling, and this beta is the rescaling of the time coordinate. So that sort of says that the time coordinate is not completely aligned with the coordinate of ADS. So once you do the mapping to global ADS, you can find what is this beta. This beta is this value here. And you can see that if you compute the mass, this beta comes here directly. So it means that you have to include this beta carefully in order to obtain the concrete mass of the black hole. And then it plays a role in the first law also. So if you also follow the randomized action and you compute the Euclidean action, we get the quantum statistical relation. It's completely is the same as always. There are no difference with the standard cases. So this follows the standard thermodynamic relations. Okay. The only thing that I forgot to write here is that the first law is a little bit different though. In the first law, Ruth and Michael Apels and David Kubitschek found that to complete the first law, usually you have this is the usual first law. In the case of something that has conical deficits like this, you have to include thermodynamic quantity is a conjugate thermodynamic quantity to the tension of the cosmic string. So you have, let's say, something like this. In the case when you have like both deficit. So the first law is fulfilled as long as you include these kind of terms in the first. Yeah. 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 So this was written in 2016. This is Gregory Apels Kubitschek. So it follows standard thermodynamic rules, except for the first law. The first law is a little bit different, and I want to keep this here for a while. So what happens in 3 dimensions? 3 dimensions is less explored. There are a few versions of the symmetric, early version of the symmetric in 3 dimensions. Mohammed Amber found in 2008 accelerating particles in 3 dimensions by slicing the symmetric in 4 dimensions in a very peculiar way. Then Astorino wrote like a sort of accelerating BTZ black hole in 2011, but just like by adding a correction of the standard BTZ black hole, like saying, okay, this is the acceleration. So it sort of works. But there was nothing like a symmetry where you can derive concretely these 2 different objects until we published our paper. I don't want to just say that I did this, but yeah, we published this paper where we did the concrete study of the symmetry in 3 dimensions. Basically, we started with the most general way of writing the symmetric, which is in these coordinates. These are called prolate coordinates, I think. Y is sort of like the inverse of the radial coordinate, and X is like the angular coordinate here. And by studying the ranges of the coordinates, you start with very general polynomials. You start fixing all the gauge redundancies of the polynomials, and then you look at what is the maximal allowed range of X here by asking that this has to have a Lorentzian signature. You can have 3 classes of geometries from this metric. So we classify this as class 1, class 2, and class 3. And then what we needed to do was to we wanted something similar to the 4-dimensional symmetric, where you have like a defect pulling the black hole. In 3 dimensions, you have to include a wall, as you cannot add a codimension 2 defect. So to include a domain wall, we have to cut and glue the spacetime in a particular way in order to get a non-trivial tension in the wall. So once you do that, we get 3 classes of geometries. In the class 1, we have accelerating particles. So we have accelerating particles that are either pulled or pushed by the wall. And then there is a class 2, which are accelerating BTZ black hole, as Astorino found, that also can be pulled or pushed by the wall. And in class 3, there are no single wall solutions. What you can find are sort of brainword type of geometries, like Rundle-Sundrum type of brainword, where you need to include 2 walls and you need to copy ADS spacetime twice. So we didn't go very deep into these solutions. So I will focus on class 1 and class 2. And also in class 1, there is a particular sector where we found like a sort of black hole. It's a very strange black hole. We call it type 1c, not very original. But yeah, this is a very peculiar black hole that I will show you later. So the class 1, yeah. Okay, so in class 1, we have accelerating particles. This is the metric. I don't want to say that much about it. It's just standard. We included this alpha, which is the same as what happens in 4 dimensions. We want to have like a sort of parameter that will be the one that connects with the time-like coordinate of the ADS space. And in the slow accelerating limit, if we look at the particles, a slow accelerating limit, we have just naked singularities. There is no horizon. This is standard in 3 dimensions. You have a sector where there are just conical singularities. The only difference is that here you can also accelerate these conical singularities. Once you accelerate them, it appears an accelerating horizon. So you have accelerating particles with some horizon here. And as there is a horizon, you can, for the rapid accelerating phase, there is a Ringler temperature. So these are the accelerating particles in the Poincare disk. It's very similar to what happens in 4 dimensions once you take the massless limit of the black hole. Here, the difference is that you are cutting a wedge over the boundary of ADS. and then you are re-identifying. So this produces the conicity of the space-time. This is for the case of a particle that is pulled by a wall. So you're pulling, and when there is negative tension, you are sort of cutting from the inside to the boundary. Big portion. So next we have class 2. This is more interesting. I will try to focus on this one more later. These are accelerating BTZ black holes. It's a 1 parameter extension of the BTZ black hole. We can see that if we take A to 0, we just get the BTZ black hole. It can be pulled or pushed by a wall, depending on the sign of the tension. And again, these solutions are produced when you copy and glue along this surface with non-trivial tension signal. So what we are doing here, this is a picture of how you construct the spacetime. You have a patch like this one. So you fix a minimum x naught, let's say, and a maximum xy, and then x max, and then you generate another coordinate patch, exactly the same, but it's like the mirror image, and then you glue over x naught, and you generate this spacetime. So there's going to be a domain wall lying on the spacetime. So you can see that this spacetime has a conformal boundary given by x equal to y, and there is an accelerating horizon. This is the class 2 pulled by pushed by the strut. So there is an accelerating horizon. And if you want to eliminate the accelerating horizon, what you can do is just constrain the value of x max in order to get something, let's say here, where you are not going to see the accelerating horizon. In the case of the positive tension, this doesn't look like this. It will look like this. So that's the only difference. And in the positive tension case, there is no accelerating horizon. So as I was saying, I want to avoid the accelerating horizon to do like a sort of a slow accelerating limit. And what I get is that I need to constrain, and I get this constraint. So this is what I will get as a slow accelerating black hole, BTZ black hole. So this slow accelerating BTZ black hole has some radius and temperature, and therefore there is entropy. Yeah, everything that is the normal thing. Okay. And what you can do is to compare with the standard. To compare with the standard BTZ, what you can do is to map into the Poincare patch. And what you can see is that this is the standard BTZ. This is what will be the accessible region at the boundary. Okay. As you introduce the tension, what you are doing is sort of moving these lines. You are deforming these lines. You are either deforming outside or deforming like inside. So you are cutting a wedge of the boundary or in the bulk. Okay. So that's the main difference with the BTZ. And then there is the class 1C. Class 1C appears when you have like a heavy, rapidly accelerating particle. Then suddenly there is if you're in the phase space of the rapid accelerating particle, suddenly the horizon becomes compact. It's very strange. It just becomes compact, but for very peculiar values of the phase space, and you have a black hole. This black hole is different to the one that I showed you about the like accelerating BTZ, because you cannot take A to 0. This only exists when you have acceleration, and the acceleration is constrained by the mass of the black hole. So again, it looks similar to the BTZ. It looks quite the same, but again, these lines are deformed, and now you cannot just get the BTZ black hole. It's a very peculiar solution. So you can do holography again. I can do exactly the same as in 4 dimensions. I can do the the holographic expansion, what I want to recall is that in 4 dimensions, there is always this dependence on the conformal representative, this omega that we couldn't find. So in 3 dimensions will happen exactly the same. So there is the boundary metric will be defined up to this conformal representative. And the problem is not exactly a problem, it's like the standard thing. If you compute the stress tensor, there is anomaly. And as there is the Weil anomaly, there is always dependence on this conformal representative. So you cannot compute holographic quantities without fixing the conformal representative. In 4 dimensions, the mass that I showed you is completely independent of the conformal representative. So here, we can do exactly the same, and we have, let's say, the Ricci scalar of the boundary metric depends on this conformal representative and actually has derivative of the conformal representative. This is because the stress tensor in 3 dimensions in 2 dimensions transforms. So you have transformations of the stress tensor. And we can get the anomaly by taking the trace of the stress tensor. We get the standard Weil anomaly. We have the central charge, the same as Brown and Queneau. And the conserved quantities here will depend on omega. So the problem is that we want to compute the mass, and we have that the stress tensor depends on omega. So we need to find a new way of doing it, or we can fix omega. The problem is that we have, how do we fix omega? We can fix omega, let's say, like Brown and Queneau, like omega equal to 1 will give you like a flat boundary metric, but that perhaps is not capturing the effects of the acceleration in the boundary. So we want to proceed in a different way. We will consider this transformation of coordinates that gives you the upper half plane. This was done by Juveni, Marloff, and Recamani in 2010, and also Casani, Gauntlet, and Martelli just very recently in 2021 for the 4-dimensional symmetric. And if we do it for the 3-dimensional, now what we are doing is we are creating the place of the conformal boundary that it was defined on this hypersurface of r and theta, phi, sorry. We are replacing that problem. We are just giving one coordinate to give you the conformal boundary at z equal to 0, let's say. But now we have a horizon that is defined not in r, let's say. Now it's defined on a hypersurface of r and theta, of phi. So we are trading the problem, and now we can compute things using this coordinate set as the holographic coordinate. We will have something like an ADM type of decomposition of the spacetime. And therefore, we can identify the boundary metric, but now the boundary metric is completely identified. There is no dependence on the conformal representative. The conformal representative is in fact fixed. And we have a non-flat boundary metric, which is given like this. G is here a function that we know what it is. So we can compute everything like as we know. We compute the stress tensor, and we can show that the stress tensor can be written in the form of a perfect fluid. In 2-dimensional CFTs, there is no viscosity, so it has to be a perfect fluid. There is no other possibility. And we check that this is exactly a perfect fluid with some pressure and energy density that depends on the value of A. Okay. And the anomaly is once again reproduced correctly. There is nothing different here. But now we can get the mass of the black hole just by integrating this stress tensor. And one important check is that if we take the acceleration to 0 in the accelerating BT set, we just get the mass of the BT set black hole. Okay. What is more interesting is that the renormalized action is a bit different from what we know from the standard literature. So if, let's say, we want to compute the Euclidean action in 3 dimensions, we will consider something like this. This is the Pallas-Surabani-Krauss action. We have the Einstein-Hilbert term. Then we have the Gibbons-Hawking term of the ADS boundary. And then we have the counter term. Okay? But the problem is that now we have a domain wall that is inserted into the spacetime, and to obtain the equations of the domain wall, we need to include something else. we need to include terms that, as you vary the action, you will get the Israel equations that are the ones that control the dynamic of the domain wall. So we need to include these two Gibbons-Hawking terms. So if we look at this picture that I show you about the accelerating black hole that is pushed by the strut, we have two internal boundaries, let's say, and we have the ADS boundary here. So we include a Gibbons-Hawking term for each of these boundaries, and then when we identify these two boundaries produce the Israel equation. Okay. So we have the tension also here. This is a standard in the literature of Brainwork. This was done by Gregory and Padilla and other people, Hermusis, Kalloberg, Padilla in 2006. So the total action should be the standard Balasubramanian-Krauss plus the domain wall. Okay. If I forget about the domain wall and I compute the Euclidean action of the metric that I showed you about the accelerating black hole, what I will get is the beta m term of the quantum statistical relation minus S minus an extra term that has contributions of the horizon of the black hole and a term that is divergent. This is a set going to the conformal boundary. So this is a regulator. So the Balasubramanian-Krauss renormalized action diverges. So I need to, if I look at the domain wall action now, the domain wall action includes exactly the same terms that I get here. I get a term that goes with the horizon and a term that diverges. And if you just put everything together, you get the standard thermodynamic relation. So in 3 dimensions, this is quite different to the 4-dimensional case. You need to include the domain wall. In 4 dimensions, you don't need to include the cosmic string, because if you go to these papers, this was answered in these papers, but nobody else wrote it in the context of accelerating black holes. Once you write the total action in 4 dimensions, and you have a cosmic string, what you will have is like this, something like all boundary of ADS, and then you will need to add the cosmic string as a tension. But the cosmic string codimension 2. So if you look at Israel equations are codimension 1. So you will have like an extra delta in the Israel equations. And once you plug back, because you need to plug back let's say you have this equation, you take trace and you plug back, you do the on-shell thing. What happens is that the tension of the cosmic string cancels each other with this term that appears here. So there is no contribution in 4 dimensions of the cosmic string. And this was not written in this paper, which is in any paper of accelerating black holes in 4 dimensions, actually. So in 3 dimensions, what we show is that these domain walls, as extend from the horizon of the black hole to the conformal infinity, it is necessary to be included into the action in order to get a well-defined quantum statistical relation. So we also did in this last paper with Felipe, we did the entanglement entropy. Just very briefly, we want to obtain the minimal area of the Ryo-Takayanagi surface. I will just skip. Yeah, I will just skip these things. But the important thing is that in 3 dimensions, usually to compute Ryo-Takayanagi surfaces is really complicated in any dimension. And in 3 dimensions, what you can do is a trick of computing the Ryo-Takayanagi surface of Rindler coordinates. So what we can do is that, as we know that we can map to Rindler coordinates, we can map these solutions to Rindler coordinates. We go to Rindler coordinates, we use Rindler coordinates, we compute the Ryo-Takayanagi surface, and then we go back to our original coordinates like this. It looks very nasty, but you can do it. And then to obtain analytic result, we want to expand for a small acceleration. And what we get is the entanglement entropy like this, where the first term is the standard term of 2-dimensional CFTs. There is a central charge. This diverges. as it should be. And then there are some subleading divergences, but these subleading divergences are a bit different of the literature. These are sort of negative subleading divergences. It means that the total Euclidean, the total entanglement entropy is sort of losing certain amount of entanglement entropy due to this correction from here. And it's quite obvious when you go back to the pictures of the mapping of these solutions to the Poincaré patch, because you are once you are constructing this, you're cutting a wedge of the boundary. So what you are doing is just you are restricting the amount of information that that is accessible to the boundary. So this correction, this is what it's saying, is you're increasing the acceleration, you increase the conical deficit, and therefore you are losing information on the CFT. So it's a very interesting result. What would have been interesting would have been to find some type of CFT with defect that will have this type of subleading behavior, but we haven't found anything. It can be also because we are expanding for little a, and perhaps this subleading behavior will be different if you relax this condition a little bit. Maybe this condition is too restricting, but it's a good first step at least. So I want to just finish with a summary. We constructed these solutions. They resemble some things of the four-dimensional symmetric, but also it has a more rich structure than the one that was previously known in the literature. We have computed holographic quantities using this ADM type of decomposition. What it will be interesting is to know a little bit more about this fluid gravity correspondence in the four-dimensional case. We also found that the domain wall is important in order to compute the correct Euclidean action. And finally, that the entanglement entropy it sort of says that as you increase acceleration, you are doing something non-trivial at the boundary. So it's an interesting result. So as future work, first, I didn't say anything about the first law in 3 dimensions. This is a little bit sensible. First thing is that if you are in 3 dimensions, you have anomaly. And as you have anomaly, the mass, as I told you, will depend on the conformal representative, let's say sigma. And therefore, this first law will not be the same. You will need to include like variations. If you take variations of the mass, let's say, you have variations of this guy. So the mass there will be like the mass plus some variations, non-trivial variations of this term with sigma. So this is not very trivial. You can sort of try to guess what it should be, this one, but we actually don't know. I think that it should be like a Casimir energy. And then the other problem is that it seems that this doesn't play the same role as in 4 dimensions. In 4 dimensions, you have that there are these 2 conical deficits. In 3 dimensions, you only have 1. So it could be that as you only have 1, maybe this is not a system in like thermal equilibrium. Maybe it doesn't follow the first law. So we couldn't find the first law yet. So there might be something non-trivial happening with the tension here. The second one is maybe we can do thermodynamics of accelerating horizons. There is a lot of developments in the Sitter space. Maybe it can shed some light about this. Some more understanding on the role of the acceleration, as I told you. Perhaps if we look at different holographic quantities, maybe we will get a little bit more intuition about how the acceleration is interacting with the boundary space-time. And finally, there are some things about supergravity. So in 3 dimensions, one thing is in 3 dimensions, as we know in 4 dimensions, this solution can be embedded into M theory by uplifting. Perhaps the 3-dimensional solution can also be uplifted to supergravity. We don't know. And the other one is that if you relax the slow accelerating condition a little bit, the cosmic string might play a role in the action once you put different values of the tensions. And as you do that, the SUSY condition, which are the supersymmetric conditions in the paper by Jerome Gauntlet and all these people, the supersymmetric conditions are encoded into the conical deficits. So there are particular values for the conical deficit in which you have supersymmetry. Perhaps if you relax these conditions, you can see where the cosmic string will appear in the action. We are not exactly sure about that. And the final thing is that you can put a black hole on the brain here. It will be more similar to the class 3, which we haven't done yet. But you can put a black hole on the brain. It would be like a two-dimensional black hole. And yeah, there's been a lot of thing going on there, two-dimensional gravity. So thank you.
Now we have time for a few questions. So
Thank you for such a nice talk. I think there is a part that is quite unclear to me, that is this use of twice the Gibbons-Hawking term. I mean, because I can imagine a much simpler setup that is a non-smooth boundary. If you have a non-smooth boundary, it means that you have a defect of codimension 2. I mean, you don't need this picture to imagine just a non-smooth boundary, a broken boundary, where you have an angle, and you don't need two Gibbons-Hawking terms to deal with that, because you know that there is a source at the corner. And the corner is exactly the source is related to the conical deficit, because it's like the one-dimensional, broken one-dimensional equivalence to a cone. So this is the Hayward term.
Not exactly. This is not the same. So
Why?
this is a third, completely third.
yeah,
It's
not-
exactly the same.
Because the third is the space-time, so you need this relative.
yeah.
It's not a point.
But when you have a non-smooth boundary, the boundary itself is codimension 1, and if you have it's not a line, it's a surface as well.
These are all space that you're gluing together. Then you need this
Yeah,
relative.
yeah.
This is not.
This is different. This is that's why it's good to look at this picture. So you have the boundary. This is the boundary of ADS that you were thinking of.
But altogether it's a boundary. It's a non-smooth boundary.
It's just like you have two coordinate patches, and you are
Call it the way you want.
For the boundary, it's not at any given point.
no. The boundary has the one Gibbons-Hawking term, which is the one of the life, like it's the balance of Riemann and Krauss term.
The boundary
Nothing
has
else.
a difference, but we are not touching that point. We're touching the surface.
Yeah.
The reflect that you have a defect is that there is something at the right hand side of that equation. There is a source,
Yeah. No, but
Yeah.
when you are.
and the source is curving, is producing the defect.
Yes, but this is produced because you're gluing two manifolds together. Then you need this relative.
Yeah. This is not like this is not a
exactly the same.
in the way that you are thinking. It will be a codimension 2 defect.
In a corner, you don't.
Yeah. If it is a corner, it is a codimension 2 defect. This is not a codimension 2 defect. This is just a codimension 1. But it's a different surface. This is like, let's say, that's why we call it gamma here, because it's a different hypersurface. It's a two-dimensional hypersurface. What you can do is actually the way of writing this, the proper way of writing this, is just with one tension. How? So you have the differential equation, you take trace here, and you will see that K is just related by its own number with sigma here. So once you do the on-shell action, K is just some number times sigma, you plug it back,
and this is nothing else. Actually, this will mix together. It will give you a number, the exact number that you need here to cancel this term is just a 1. This comes with 2. You plug it here. This comes with a minus sign. This comes with plus. You get the correct sigma here. So it's the same thing as Vilenkin. This is the original paper about cosmic strings, but in 3 dimensions. This is a tension. This is like a Nambu-Goto in 2 dimensions. Nothing else. It's not a 2-dimensional 2D defect as
Sorry, but the boundary that you have there is a smooth boundary
It's
because
smooth boundary,
when you induce going to the linear of the when you induce a domain wall there, usually this actually changes the character of the CFT. You have a BCFT in this case. You have a so
yeah.
I would expect
Yeah.
you so.
That's true. It can be non-smooth, but that doesn't. You don't need a codimension 2, like a codimension 2 term to regularize this. The only thing that you need is just an action that gives you a well-defined variation principle. Nothing else. If you don't include this term, you don't have variational principle because you don't have Israeli equations. Yeah, and so at the beginning, if we tell the entire story about this thing, we were computing with Felipe, and we were getting this term. We were like, "What the fuck is happening here?" And we are using the holographic randomization scheme. Why are we getting this term? And then we start to like say, "Oh, maybe it's a Hayward term because the boundary is not smooth." Hayward term will be codimension 2. What is the term in codimension 2? It would be like a point here. No, you don't need it because the only thing that you needed to ensure, yeah, you're removing the point that this point, but that is not elegant. I mean, what you want to do, but you don't need to do it. Yeah, that's the thing. You don't need to remove one point because it will be why you will remove one point only because you know that it is like non-smooth. The only thing that you want to care, you need to care is about the physics. The physics is you want equations of motion, and then you want Israeli equations that will give you the dynamic of this domain wall that you're putting. And just by ensuring that, you are getting the correct result. This is necessary. Otherwise, you don't get the Israeli equations. Yeah, because if you include the Hayward term, how do you get this? Yeah. Yeah. This is equations of motion. You have equations of motion on the bulk, equations of motion. Yeah. Even, yeah, that's true also. This goes from the horizon to the... Yeah. 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 I mean, this is equations of motion. This is well defined variational principle. Nothing else. Yeah, this is the standard thing of Brainware. I mean, people have been doing this. That's the funny thing. This is in papers of 2001. So people been putting brains, like you can put like DS brains and stuff like that, and they were using these kind of things. And yeah.
But even if okay,
But yeah, we can do it here in the and on top of that, we have the conform about nothing.
but okay, but I think that the question is like, why would I include something else if I already have the correct result? I mean,
If you have a non-smooth part, we consider.
Yeah. Yeah. This is geometry. I mean, you construct a space-time. Yeah.
Separation of the three boundaries.
Yeah.
There's a jump of 23, but how you will not consider that? How you will treat that exactly the same as the other. That's not it. So you need to consider it.
I mean, yeah.
So, under, please. Okay, thanks again.
Tú haces. Vale, gracias.
No, pero volver a pero en el parque